Climate change and adaptation. Second unit, observed changes and its causes. The first module of that is observation of the climate change patterns. Here is just one of the many strategies used by scientists in exploring the climate changes. The climate change study starts with collecting the experimental data. For that, one has to investigate the study area by preparing and analyzing the available data. And the objective of that is to identify the sensitive factors. Often satellite imageries are used for that. Now, once you get experimental data, then the focus goes to the analysis of the sensitive factors to be which are detected here. Now, the sensitive factors, you have to explore the spatio-temporal characteristics of these factors, which need to further explored for any trends or any anomaly. An objective of such studies is to probe the link of the sensitive parameters with the potential climate change. Now the focus is on selection of the suitable strategies, equipments and recordings of the results that need to be focused for testing one's hypothesis. The sensitive parameters are known, factors already known. Now you have to explore how to detect that, how to identify that, how to record that, what strategies to follow, and for that we need to have a hypothesis based on the global scenario, which is and what are the contemporaneous studies available, what are the studies available, where does it stand, what are the gaps, what are the frontiers. Then for this the objective should be to evaluate the most robust algorithm for testing the algorithms, testing the hypothesis what you proposed. So some conceptual algorithms is developed here to satisfy the studies we carry out. We also, new data sets may be used, which is not used for modeling. It has to be used for testing and training the data. And then the purpose of that is to validate and calibrate iteratively the models with best accuracy and precision and provide forecasting. At this stage, it is necessary to develop a more integrated conceptualizations using multi-observational platform or spatio-temporal platform, because it is observation at one location on case study. It has to make it multi-observation at different locations. So focus shifts. And then for multi-observation platforms, we need to require networking with and developing more integrated concept development, interact with other scientists working in these fields, and other observation, similar location, dissimilar locations, comparison of that, integration of that, differentiation of that, all the components comes here. And here the objective is to evaluate the model robustness and application of the developed model or integration of the available models, so to get something which is applicable over a generalization time. Sometimes it may not be possible. In that case, you have to give the strategic specifications or limitation within which the model can work. Finally, the simulation of developed model forms the most important deliverables. This is what final deliverable which can be utilized for further studies. So this needs final refinement and establishing a conceptually sound and proven feasibility expert system. And then the final knowledge needs further evaluation of expected or potential scenarios for assessment, remediation, adaptations. So that this is what the scenarios which works for different situation, and that's what final prediction can be used. So the central part we identified is covers under results, and previous left part comes under the research contents, and finally the right part comes under the scientific objectives. So for these objectives, you focus on the similar results you're finding, and then the research contents defined accordingly. So this is one of the standard strategy used by many of these climate researchers. Over time, there has been a lot of changes in temperature, precipitation, sea level rise, and we'll just have a simple exploration of that. There have been more high temperature has been high, and there have been more droughts, and there have been wild weathers and changing the rains and snow patterns. There has been less snowpacks, shrinking sea ice, melting glaciers, thawing permafrost. We have the increasing ocean acidity, warmer ocean, rising sea level. This way, a whole range of climatic changes has been witnessed by the planet now. We'll explore each of them little more closely. Higher temperature. Greenhouse gases are trapping more heat to the Earth's atmosphere, which causing large increase in the average temperature of the all over the world. What is happening now? The temperature have risen during the last 30 years, and 2001 to 2010 was the warmest decade ever recorded in the history of the planet. As the earth warms up, heat waves are becoming more and more common in some places including United States and Canada, and heat waves happens when the region experiences high temperature for several days and nights. And what will happen in future then? If people keep adding greenhouse gases into the atmosphere at the current rate, the average temperature around the world would increase by about 4 to 12 degree Fahrenheit by the year of 2100. If you make big change like using renewable energy and resources and replacing fossil fuels and also so forth, increase will be little lesser, maybe 2 to 5 degree Fahrenheit. Why does it matter? Higher temperature means that heat waves are likely to happen more often and last longer too. Heat waves can be dangerous, causing illnesses such as heat cramps and heat strokes or even death. Warmer climates can also lead to a chain reaction of other changes around the world. That's because increasing air temperature also affects the oceans, weather patterns, snow, ice, and plants and animals. The warmer it gets, more severe impact on the people and the environment will be. Now we'll see some more implication. Actually, the fundamental point is increasing temperature or the climate change. So now some more implication of that we'll explore. This is what we are seeing that the plots of showing how over the years that climate changes is taking place. Of course, there is fluctuation up and down throughout the season itself, but over the years it has increased very high. The upper figure provides the CO2 concentration, carbon dioxide concentrations in the atmosphere in parts per million, and bottom is the temperature. As you can see, very closely resemble each other. So carbon dioxide concentration and seems to be directly affecting the temperatures, and there are several findings are there. Various measurements of global temperature has been done. The first one is GIS. You can see all of them very close. GIS is located in Columbia University in New York City. The institute is a laboratory of Earth Science divisions of NASA's Goddard Space Flight Center and is affiliated to the Columbia Earth Institute and School of Engineering and Applied Sciences. The second plot, which is also very much closely resembling that, is hard crust. Is a data set of monthly instrumental temperature records found by combining sea surface temperature records compiled by Hadley Center of UK and the land surface air temperature records compiled by the Climate Research Unit CRU of the University of East Anglia. Then NOAA, National Ocean and Atmosphere Administration. This is an American scientific agency within the United States Department of Commerce, which focus on the conditions of the ocean, measure waterways, the atmosphere. NOAA warns the dangerous weathers, charts seas, guides, and uses the protection of ocean and coastal resources, and conducts research to provide an understanding of an improvement of the stewardship of the environment. Then RSS, that refers to remote sensing systems, Another scientific research company actually, which is located in Northern California, specializing in satellite microwave remote sensing and the Earth System Sciences Center. The New Age, the University of Alabama in Huntsville, which releases climate report regularly based on the climatological teams. So now we can see that there are different methods they used for finding, and all of them very closely resemble the so far results are concerned, and showing the global temperature is actually on increase. And we can see it's not just matter, and there is changes also. The cold seasons has been shifted, so now less cold weather is available, and the previous climate has shifted towards the right, as you can see, and the more heat weathers are coming. So the peak is changed, shifted, and the duration also shifted. This is the probability of occurrence also. Now what happened? The changing the rain and snow patterns. As the temperature rises and air becomes warmer, more moisture evaporates from land and water into the atmosphere. More moisture in air generally means we can expect more rain and snow, which is called precipitation, and more heavy downpour. But this extra precipitation is not spread evenly around the globe, and some places might actually get less precipitation than they used to get before. That's because climate change causes shifts in the air and ocean currents, which can also change the weather patterns. So what is now happening is the sequence. Uneven precipitation, not just increased precipitation, uneven precipitations, different locations. On average, the world is already getting more precipitation now than it did in 100 years ago. 6% more in the United States and nearly 2% more worldwide. The effect vary by region though. For example, states in the northeast are getting more precipitation than they used to get, but on the other side, like Hawaii, they're getting less precipitations. So what will happen in future? Precipitation is expected to increase in higher latitude and decrease in areas close to the equator. The northern United States will become wetter than the south, particularly in the southwest will become drier. Why does it matter? Too little or too much water can cause a problem. In many places, people depend on rain and snow melt to fill lakes and streams and provide source of water for drinking, watering crops, and other type of uses. However, heavy rain can cause flooding and unpleasant droughts. Another place. Yes, let's explore the droughts. A drought is an extended period of dry weather caused by a lack of rain or snow. As temperature rises due to global climate change, more moisture evaporates from land and water, leaving less water behind. Some places get more rain or snow to make it up, but other places become drier. What is happening now? Since 1970s, droughts have become longer and more extreme worldwide, particularly in tropics and subtropics. And what will happen in future? Droughts are expected to keep getting longer and more severe. The US Southwest is particularly risk for increasing droughts. And why does it matter? A drought means there is less water available for drinking, less water available for watering the crops, less water available for making electricity or hydroelectric dams, and so many other uses. For example, an ongoing drought in US Southwest is straining water supply in the states like Nevada and Arizona, where water is already very scarce, and the same situation is continuing all over the world. There is a potential for the droughts in the end of the century based on studies and simulations. You can see high risk areas, which are most reddish in colors and is spreading all over the world. India comes mostly in moderate risk. You can see this green colors. Then warmer oceans. Atmosphere affects the oceans, and ocean influence the atmosphere. As the temperature in the air rises, the ocean absorbs some of the heat and also become warmer. What is happening now? Overall, the world's oceans are warmer now than any time, any point in last 50 years. The change is most obvious in the top layer of the ocean, which has grown much warmer since late 1800s. The top layer is now getting warmer at a rate of 0.2 degree Fahrenheit per decade. And why does it matter? Warmer ocean affects weather patterns, cause more powerful tropical storms, and can impact any kind of sea life, such as corals and fish. Warmer oceans are also one of the main causes of rising sea level. Here you can see how the average global sea surface temperature of the world it has been increasing over time. 1971 200 average, it was less than 0.5 temperature change, but now this temperature of this water has increased so much high, and every degree counts. We'll see that, explore that. Rising sea level. As water gets warmer, it takes up more space. Each drop of water can only expand by a little bit, but when you multiply the expansion over the entire depth of the ocean, it all adds up and causes sea level to rise. Sea level is also rising because of melting glaciers and ice sheets, which are also adding more water to the ocean. So what is happening now? Over the past 100 years, the average sea level around the world has rose by 7 inches. What will happen in the future? If people keep adding the greenhouse gases in the atmosphere, the average sea level around the world by the end of the century, that is 2099, could be anywhere from 7 to 23 degrees higher than what it was in 1990. Sea level could rise even more if big ice sheets in Greenland and Antarctica melts even faster. Rising sea level is a threat to people who live near the ocean. Some low-lying areas will have more frequent flooding, and very low-lying lands could be submerged completely. It has already happened. There are some islands even close to in India, close to Sundarban. They have already completely submerged into water, even habitat islands. Rising sea level can also harm important coastal ecosystems like mangroves, forest, and coral reefs, which affect entire marine life. So, why does it matter? Because with rising sea, we'll have less water available for drinking water in crops, and simultaneously we'll have more flooding when submergence low-lying coast and deterioration of the coral ecosystems like mangrove forest and coral reefs, affecting the planetary sustenance. You can sea level rise over the world over the years in the world. You can see here there is a drastic increase, and in fact this we can see that the two curves are there, which gives the confidence intervals 95, 87, 95 confidence interval, and actually both of them very close. That means it's almost precisely increasing. That much variations possible. Wilder weather. Hurricanes and other tropical storms getting their energies from the warm ocean water, because all this depression on the ocean is what causes the cyclones and hurricanes and other type of tropical storms. As the top layer of the ocean gets warmer, hurricanes and other tropical storms get stronger, and faster winds and heavier rains. Because higher temperature and increased evaporation, climate change causes other types of storms to get stronger, thus adding more water to the oceans. What's happening now? Over the last 20 years, hurricane and other tropical storms in the Atlantic Ocean have become stronger. Since 1980s, United States has also experienced more intense single day storm, which are dumping lot more rain and snow than usual. And this scenario is continuing in the other countries as well. We'll see that. Um, what will happen in future? As the climate gets warmer, heavier rainstorms and snowstorms with more precipitation than normal are expected to happen more often, and the hurricane around the world keep on getting stronger. Why does it matter? Hurricane and other storms can cause flooding, damage buildings, roads and other structures, harm crops, and put people's lives in danger. You can see how the hurricane strength has been overrise. The power dissipation index is uh, the red curve, and the dotted ones is the ocean surface temperature, very closely related. As surface temperature increasing, the power dissipation index will be more, so there is more chance of hurricane strength. Then wilder weathers. Carbon dioxide is added to the atmosphere whenever people burn fossil fuels. Ocean plays an important role in keeping Earth's carbon cycle in balance. As the amount of carbon dioxide in the atmosphere rises, the ocean absorbs a lot of it. In the ocean, carbon dioxide reacts with seawater to form carbonic acid. This causes the acidity in the seawater to increase. What's happening now? Over the last few decades, the amount of carbon dioxide dissolved in the ocean has increased all over the world, and so has the ocean acidity. And what will happen in future? Over the last few decades, the amount of carbon dioxide dissolved in the ocean has increased all over the world, and as I mentioned, and acidity also has increased, and is going to increase further. Why does it matter? Increasing acidity will make it harder for the corals to build the skeletons and shellfish to build the cells they need for protection. And coral and shellfish play a very, very crucial role in maintaining the aquatic ecosystems. Corals are particularly provide the homes and habitats for many other sea creatures. So this is how the carbon dioxide content in the ocean, dissolved carbon dioxide content in the oceans, is measured over time. You can see how some Bermuda, Canary Islands, and Hawaii, how it's over the period of time it is keep on increasing. Seasonal fluctuation there, but it keeps increasing. This small figure there is showing that pH scale, how it reduces become acidic and when it increases become alkaline. Another problem we face is shrinking sea ice. The Arctic Ocean around the North Pole is so cold that it is usually covered with ice. In winter, the area covered by ice become bigger, in summer it gets smaller. If the air and water are warmer than usual, the Arctic sea ice will melt much more than usual during the summertime. This melting and building up is a regular process, seasonal process. But now it will be warmer, then melting will much more than what is expected. What happens now? The amount of summer ice in the Arctic Ocean in recent times is the smallest it's been since the scientists are studying the satellite to measure the areas covered by the ice back to 1970s. What will happen in future? Overall, the Arctic ice will continue to shrink in the coming decades. However, the amount of the sea ice varies from year to year depending upon the local temperature, wind pattern, and ocean currents. What does it matter? Many animals depend on sea ice for their homes, for hunting grounds, and the native peoples in the Arctic eat these animals for the source of their food. In addition, ice and snow reflect a lot of sunlight back out to the space to help to keep the planets from getting too warm. If there is less ice, the Earth will absorb more heat, more energy from the sun and gets warmer. The reflection part will be reduced. This is an example of positive feedback loop. Positive feedback means which happens when the warming causes change that lead to further warming. Positive. Lead further more unstable situations. So sea ice extent, you can see reducing over time annually. Similar melting glaciers. So there is a, just like rainfall, there is snowfall. When snow is consolidated, become ice. When ice starts moving, it becomes glaciers, moving ice. So melting glaciers are large sheets of snow and ice that is found in the land all along for years. They are found in western United States, Alaska, mountains of Europe, Asia, and many other parts of the world. Warmer temperature cause the glaciers to melt faster and than they accumulate new snow, because glaciers are made up by deposition of the snow and which compact become ice, and over pressure of the ice the glaciers start melting off, and that's what the source of many of the rivers. When our Ganges comes from Gangotri glaciers. So now when glaciers start melting further, what will happen? What is happening now? Glaciers all over the world have been melting at the rate, at least for last 50 years. The rate of melting is speeding up. Many glaciers in Alaska and other parts of US have shrunk very dramatically. What will happen in future? It will continue with increased rate of melting, and in fact some of the glaciers may completely disappear. What does it matter? As glaciers and giant ice sheets and the Greenland Antarctica melts, they add more water to the ocean, which causes sea level to rise. So these are the photographs in Alaska. These are glaciers, 1958, and here is a glacier, 2003. You can see so much part is completely gone. Easily permanent ice sheets, but it's reduced so much. Less snowpack. What is snowpack? Snowpack is usually, it refers to total amount of snow or ice on the ground at any time, how much ice and snow available on the ground. In high mountain ranges and other cold places, snowpack builds up in the winter and melts in the spring or summertime. It need not be compact like glacier, it's just about a snow which is available on the snow or ice available on the ground. As the world gets warmer, some places will get more rain instead of snow, because temperature increasing, so snowfall will not be there, rainfall will be more. So the snowpack won't be as deep. Plus, when air becomes warmer, snow also melts faster, so there will not much deposit of snow. At the same time, it's melting also, melting become faster. So what is happening now? Many places have less snowpacks than they used to, and the snowpacks is and they're melting earlier snowpacks very fast. What will happen in future? As temperature keeps on getting warmer, snowpack is expected to continue to shrink, most in North America and many hilly areas around the world. Why does this matter? When snowpack melts in summer and springtime, it provides fresh water to river and stream, and it fills reservoirs that supply drinking water to cities and towns. Snowpack is also important for winter sports like skiing and snowboarding and other games. So all of them will be reduced drastically. So this is 1970 to 2004. You can see how much snowpacks has been decreased over time. So the gaining 0.2 to 3, right side blue is very less, and losing 2 to 4, red is increasing. Especially losing 0.25 to 1 is maximum spreading out. Then thawing the permafrost. Permafrost refers to a layer of soil or rock that is frozen all the year round. Perma means permanent, frost means frozen. So permafrost is found throughout the Alaska and parts of Canada and other countries in the far north. Note that the permafrost is not a barren land. Plants also still grow on the soil and the surface, which is not frozen during the summer part of the year. However, there may be thick layer of permafrost underneath. Air temperature rises, so does the temperature in the ground, which can cause the permafrost to thaw or melt. So the still soil will be there in the ground. Top, bottom, ice will be there permanently. They don't get melted. So permafrost, you can see a pictures here. You can see here active layers is there, soil is there. Below that, there will be ice wedges will be there. So permanently. So that's why permanently frozen. So doesn't mean the plants will not grow. Plants will grow on the top, but bottom ice will be there. It's not like glaciers or snowpack. So what will happen in the future if permafrost are getting melted off? Thawing means melting. They melt off more and more. What will happen? The temperature keeps getting warmer. Permafrost will continue to thaw. For example, we can see by 2100, permafrost will expected to be very, very low. What does it matter? Why does it matter? Since it's going to continue further and further as in the future. So when permafrost melt, the land above it sinks and changes shape. Sinking ice can damage building naturally because the foundation is disturbed, so stability disturbed. So building structures will get damaged. Infrastructure such as roads, airports, water and sewer pipes, it also get affected by that. It also affect ecosystems. For example, it can also lead to the trees and forest lying over the permafrost, which is leaning or falling over because the permafrost underneath the items is melted. So actually those areas ice will always there, permafrost, and but on the top of that everything will be as usual, soil, structures, forest, everything will there. Now once this ice start melting off, then everything will become disturbed. Alaska's permafrost, you can see continuous permafrost was there, yellowish part. Some permafrost is there. Seward Peninsula, and later this century we are expecting that no permafrost will be there. See red color, no permafrost will be there. Previously, very few areas no permafrost. Then these large scale variability are affected by mostly wind patterns, because temperature affect the wind affect the sea waves and currents, and combined with all the three factors combined together can create multiple factors, and that's a very complicated variabilities takes place. You can, there are the different pictures of the wind which is the driving force behind that. Here is a bar chart which is, and this forcing, so now forcing agent is that agent which forces the climate to change. So radiative forcing, like hatched, the force because of radiations, and the effective radiative forcing solid for the period of 1750 to 2011, where the total effective radiative forcing delivered from the Intergovernmental Panel of Climate Change fifth assessment report. Uncertainties 5 to 95% confidence range are given in radiative forcing dotted lines for the uncertainties, and for the effective radiative forcing it is solid lines. The lines are there, so they show the uncertainties in that. Volcanic forcing is not shown because it is volcanic is natural and it's intermittent, exerting force only over a few years for eruption during the industrial area. So net forcing over industrial area is negligible. So these forcing are the persistent pressure exerted by different type of forcing agents like greenhouse gases, ozone, stratospheric, water vapors, or surface albedo. Albedo means reflectivity. This contrails, aerosols. So all these things, what are the forces they create, put on the climate. Now that there is something called climate sensitivity. To evaluate the sensitivity of the climate, climate sensitivity describes the effect of increasing carbon dioxide, any greenhouse gas, that have over the global near temperature surface air temperature. Because we are seeing that global temperature increase is the main parameters behind that, so everything is connected with that. So sensitivity, how this global temperature affected by the particular parameters. This characteristic of climate change emerges from many feedbacks of a wide range of timescales following the initial intermediate change in radiative valence in the atmosphere. So now the sensitivities, the contribution of each parameters on the global warming, and at the same time there is a feedback. Feedback is, it occurs when a portion of the output from the action of a system added to the input and subsequent alters the output. So there is input which is causing a process and some output coming, and now a part of the output again called gain, which goes back and again contributes to input. Now the gain is reducing the as a contributing input, whether it is positive gain or negative gain. If positive gain, then output will keep on increasing. Negative gain, output keep on decreasing. So the result of the loop system can either be amplification or damping of the process depending on the sign or gain of the loop. The sign of the gain, it decides whether positive or negative loop. Amplifying feedback is positive, damping feedback is negative. We'll see some feedback. Ice albedo feedback. So cold temperature leads to expansion in the areas covered by ice, which tend to be more reflective than the water and vegetations. The ice will reflect more, so cold create more ice. So this causes reduction in the absorbed solar radiation, which causes more cooling, because more reflected, again less heat will come in, again more ice will available. So this way it keeps on increasing more ice content and lesser temperatures. Is it positive or negative? This is what happens, increasing. Check this sign of the feedback. Is actually increasing the cooling or decreasing cooling? It's increasing, right? So it's positive. It's contributing more, gaining more. Same process gaining more. Now what happens when global warming leads to melting of the ice and snow, and thus reduced reflections? When global warming happens, what happens? Ice and snow melts. So because of that, reflection also reduces, less available, which causes more heat is coming. Again it melts further. Again further decrease. Again further heat is coming. Similar to that process, but here warming, ice melting, reduce albedo, reflectivity, and more insolation or more absorption of solar heat, and more warming. This is positive or negative? Note this sign, because it is increasing again the same process, input, contributing more to input. So yes, this is also positive. Now you can see, just by same both way it is positive feedback. If we allow it to cool, then automatically ice will grow, it will maintain a positive feedback for cooling. When allow it to heat, again positive feedback for heating. In nature both takes place, heating and cooling, so it's element balance. But now the present process is replacing the previous. So we are finding right hand side feedback is intensifying further global warming, which is more unstable situations. Let's go to the next one, water vapor feedback. The capacity of atmosphere to hold water vapor, called specific humidity, which increases exponential temperature. More temperature, more water vapor it can retain. Warming is thus accomplished by moistening or even water vapors, which leads to more warming due to enhanced water vapor greenhouse effect. Because when heating more, so water vapor comes to is the water is vapor from the water is now increasing humidity. When humidity increases, then again because of that temperature also increases, warming more take place, because it's also water vapor is also a greenhouse gas. So because of that, what happens again, further heating take place, and as heat, saturation point also increases, so more moisture it takes it up. So this way it's keeping on increasing more and more. So stipulate the clouds are there on the top surface, so sunlight is coming, this bigger source, and what and water vapor comes, again the cloud stops it, and it will, because the heat, it will absorb more water, so again heating further take place. So that way the moisture keep on return increasing further and heating increasing further, both increasing, both are assisting each other. So this is positive. On the other hand, if cloud level is reduced, for example temperature increasing, which increase the cloud cover, increasing cloud cover will reduce increase, because cloud cover increases, solar radiation will decrease because it stops that, and it limits the warming, because radiation coming limit warming, especially for the cloud in lower stage. What happens, they will not allow sunlight to come through. At the same time is cool, because sunlight is coming through and it cannot retain the cooling. So in that case, what happens, more of this heat will go back, because less is coming, less sunlight is coming, and what is going, it is mostly passing through the clouds, because lower clouds, and which reflects back sunlight. At the same time, it allows this moisture to go out. So in that case, what happens, it will be negative feedback. Now look at this too. Just an altitude changes can make feedback changes. One case positive, one case negative, just by shifting the cloud positions. So we have seen how the very altitude of occurrence of cloud can transform the type of feedback. As you already know, the whole range of parameters guide the formation, transportation, and condensation of cloud, such as air temperature, wind speed, directions, continentality, humidity, seasonality, global wind, current circulation patterns, and so forth. And all of the parameters by themselves are in flux. I'm sure you can visualize how sensitivity of the climate in equilibrium and what is the risk of its perturbations. Here is a demonstration showing simultaneous operation of multiple positive feedbacks at acting against the natural climate equilibrium. Positive feedbacks always destroy equilibrium. As there is a burning of fossil fuel, you can see the fossil fuel burning in the black box, and following from there. There is rise in air temperature, which melts permafrost, which again raises air temperature. That leads to further ice cap melting. At the same time, it also leads to subsea frozen deposits of methane release, because when this melts, at the time the methane deposits, they get released, methane hydrate deposits, releasing the methane. Permafrost melting also lead to additional release of methane and nitrous oxides, who themselves are also greenhouse gases, leading to further rise in air temperature. With the reduction of ice caps, there is a decrease in global albedo, thus again increasing available solar radiations to increase the temperature further. Additionally, the molten ice and subsequent sea level rise lead to decrease in the ocean salinity, and thus slowing the ocean. Once the salinity decreases, then what will happen? They slow down the deep ocean currents, which are driven by the thermohaline gradients, which coupled with the increasing global temperature cause the increasing occurrence of severe weather and so forth. Now you can see it's a very, very dangerous situation. So everything is positive feedback and creating total climatic disturbances. Climate sensitivity, just have a is measure of is a how much the Earth's climate will cool or warm after a change in the climate systems. For example, how much it will warm in doubling the carbon dioxide concentrations. Scientists use a whole range of models, starting from zero-dimensional energy models, and their whole idea is to and evaluate that how it is contributing to the, as I mentioned before, contributing to the global warming. Climate sensitivity refers to the degree of cooling or heating experienced by Earth climate by doubling the carbon dioxide concentration. That is how much required for certain types of processes to double the carbon dioxide content. That is carbon sensitivity. Equilibrium carbon sensitivity is a variation of temperature corresponding to doubling the carbon dioxide, because you are saying everywhere the temperature increasing. So temperature corresponding to carbon dioxide doubling. So compare any activity based on that. Since the climate sensitivity is simply a parameter which can be changed in a model, so sensitivity is a parameter, you can change the model. So scientists can do so many simulations using different values of climate sensitivity and observe which values fit the best with this observation. That's how they do. They use some parameters and keep on changing parameters to match with the present situations. That's how sensitivity parameters, climate sensitivity, is estimated. So there are some of the examples of the evidence of climate changes. Global temperature versus model simulations during the modern instrumentation era, based on experiments done over modern period back to 19th century during the observation of global mean temperature. This is also available, you can see them. Then here the deep ocean temperatures is a model simulation during the past half, showing the uncertainty in the range in observations. During the shorter period in the past half century, when deep ocean temperature observation are available, experiments are done to compare the model simulated change in ocean heat content and that which has been observed. So you can see. And now the bottom left one is a proxy reconstruction of the northern hemisphere temperature over past millennium compared against the model simulations. So you can see all of the models are very close. So here the radiative forcing estimates. Radiative forcing means radiations, heating radiations. Estimates to, which is used to drive the climate model simulations of past millennium, separated into volcanic impact on the top, solar intensity impact on the middle, and human impact on the bottom. These are the various radiative forcings. This refers to the longer period of the past millennium during which temperature changes, documents, and based on past climatic proxy data. It is possible to compare the simulated and observed over a long range of time, provide a potentially tighter constraints on the climate sensitivity. The computer model simulate that it is driven by long-term estimates like ice core evidences and natural volcanic or solar forcings, as well as anthropogenic forcings. So these are the various methods they use for exploring reconstructing the climate and the temperature profiles over time and simulations. The overall evidences from all these different lines, you can see the different constraints by past transient temperature solutions, temperature evolutions over time. All of them by various studies with references given, and evidences regarding both human caused and natural climate changes over a broad range of time scales. Is that The equilibrium climate sensitivity likely to fall within the range of 1.5 to 4.5 degrees centigrade per doubling, with most likely the range will be around 3 degrees centigrade per warming. So last 3 sets of figures, these are giving the estimate of the equilibrium climate sensitivity based on the studies. The past variability, top one, current day climatic data is the bottom one. So let's have a quick glance of different threads, some of the threads you have seen discussing all along now. Global warming consequences, flood, droughts, change in the patterns. In Paris Protocol, it is mentioned that the temperature should be well below increase to 1.5 degrees maximum, not 2 degrees too high. Why? Because the albedo is increased and they will decrease drastically if you reduce. Similarly, 1.5 degrees centigrade, the sea level rise is less or equal to 77 centimeter. 2 degrees centigrade, 10 more centimeter increases, just 0.5 degree. 14% affected by 1.5 degrees centigrade, and heat waves will go to 37% by 2 degrees centigrade. 7 to 80% affected. Just in 1 degree 0.5 increase, more than 99% will be dead coral reefs dead. When air pollution episodes 2 degrees centigrade, 1.5 millions will affected by that. So with this increasing activities, over dependence in energy, is it possible? Yes, it is possible. If we make a definite efforts to make net negative global emissions, is possible, and many countries focusing on how to accomplish that. Thank you.